operations of linear algebra this semester. I have taught it before. I'll probably teach it maybe not next semester, that's for sure, but the following one, maybe. We'll see. Okay, what am I doing? Oh yeah, I'm doing this one. So yes, so make sure you read the exam instruction before doing the exams, because I did change the exam instructions. So make sure you read them. And I noticed that no one has taken the exam yet, which is fine. I'm not mad about it. That's fine. I understand you guys want to prepare for it, but I'm just letting you know that before you do the exam, read the instructions, because you may see some change in there. Okay. And other than that, we'll pretty much continue on from what we did last time. And again, I posted the exam, not the exam. I posted the key to the quizzes so you can see if the way you did your quiz, you showed enough work. I haven't graded the quizzes yet because I haven't even downloaded them yet, honestly. I haven't even started grading them. So keep in mind that your quizzes, they'll get graded this week. I just haven't had the time to grade them at the moment. I'm praying for you. Oh yeah, 3 exams. Yeah, sounds about right. That's college life. Sounds about right. Well, in hindsight, well, hopefully my exam, you have an entire week to decide when to do it. So that's hopefully that gives you a little more stress, a little bit less of stress. Hopefully. Okay. So the last thing we did, but let me share my screen. Was this, and I believe this is the last thing we did, which was section 6.1, I want to say. Can't remember the section number right now. Yes, 6.1. Where we did the basic idea of counting. That's what we did. The basic idea of counting. Nothing, we're gonna talk more about that later on today, but this is just a basic idea of counting. Any questions so far? Just trying to make sure. Okay. So we did this, we did this. So now we're going to do section 6.2 and 6.3. Those are the only 2 sections that we're going to do today, 6.2 and 6.3. Okay. And again, I'll say this again, because I know, and you're probably going to hear me say this multiple times. Before you do the exam, read the exam instructions. I changed one of the instructions on the exam instructions. Not that I changed, let's just say I added an instruction. So make sure you read the exam instructions before taking the exam, okay? And then when you do take the exam, make sure you read the instructions. Okay. Okay, now let's go over section 6.2. Okay, section 6.2. So here we go. Let's suppose you have I don't remember exactly what it's called, but let's say you have a shelf that has individual cubicles, something like this. So an n by n shelf. But let's say this shelf has a specific amount of cubicles. So let me draw this out. So 1, 2, 4. So let's say like that. Let's keep it small for right now so everyone can see this. So 4. And let's go with 1, 2, 3. Yeah, this should be good enough. So 1, 2, 3, 4. 1, 2, 3, 4. So 16. So a 4 by 4, 16. So all of these are cubicles. Good. Okay. Now we have 16 boxes. That's another way you could look at it. 16 boxes. So all of these are boxes. And let's say you have 17 pigeons. Now, so these are called pigeonholes because they're going to house a pigeon. Now, each pigeonhole is going to have at least one pigeon. Okay, so if I put a pigeon here, here's a pigeon. That's a horrible pigeon, but whatever. Here's another pigeon here. Let me copy it. Here's a pigeon here. Here's a pigeon here. Pigeon here, 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 and here. But how many pigeons is that in total? Yes, pigeon like a bird. How many pigeons do we have here in total in each one of these pigeonholes? How many pigeons do I have here so far? 16. But how many do I need? 17, right? I need 17. Well, if there's supposed to be 17 pigeons, but there's only 16 boxes, then one of these boxes will contain at least one pigeon. Let's say this box here chosen at random. Right there. Does everyone agree with this? Does that make sense? If I have 17 pigeons and 16 boxes, there's at least one box that will contain, there's going to be at least one box that will contain at least one pigeon, or will contain two pigeons. And in this scenario, this is the box here. This is known as the pigeonhole principle. That's what this section is about, the pigeonhole principle. And the basic idea of the pigeonhole principle is that if you have K objects that are needed to be placed, if you have K objects, K plus 1 objects, I should say, if you have K plus 1 objects that need to be placed in K objects, chances are that one of those objects will contain at least one or more of the objects in it. If each one of those objects needs to contain one. That's the idea, the basic of the pigeonhole principle. That if you have K plus 1 objects that need to be placed in K boxes, then there's going to be a box that will contain at least one of those K objects, meaning it can contain one or two or more, depending on how many objects you have. That's the pigeonhole principle. That's a basic idea of the pigeonhole principle, but I'll write it out. The pigeonhole principle. Another name is the Dirichlet. That's a German name. I'm sure I'm not pronouncing it right. Drawer principle. Now, what does this principle state, like the actual definition? if k is a positive integer and k plus 1 or more objects are placed into k boxes, then there is at least one box containing two or more of the objects. And that does make sense. Imagine, like, let's say you have a class of students of 25 students, and you yourself, including, let's just say students, so let's forget the teacher. So you have 25 students, and you're one of them. And you buy a bag of candy of, let's say, 51 pieces, right? Would there be someone who has more than the other people? If so, how many? According to the pigeonhole principle. Let's say there's 25 students, including yourself, and you buy a bag of 51 Reese's Pieces, whatever candy you want, and you hand it out where each person gets one, at least one. There's going to be, will there be someone who has more than everyone else? If so, how many would they have, at least? I wouldn't say two, but you're close. Not one. Three. Right, it'll be three, right? Because if you have 25 students, including yourself, so you're within amongst the 25, and you have 51 candies, 51 pieces of candy, and each person's going to get one for sure. So you hand it out one by one. Okay, this person gets one, and then you go through the first 25. That means you have 26 left. So you go again, get everyone another candy bar. You have, including yourself, that's 25 again, and you're left with one more. So one person, there exists at least one person who's going to have at least three candies. Does that make sense? By the pigeonhole principle, assuming everyone is getting a share. Okay, sweet. Most likely that person who might be getting the other candy may be yourself. You may be like, I'll get more than everyone else. Or maybe it's someone you like. I'll give them that more, you know? But especially during this time, everyone wants a candy. Trust me, I completely understand. But that's the pigeonhole principle. That's the idea. That if you have k plus 1 objects and k boxes, there's going to be a box that's going to contain more, at least, there's going to be a box that contains at least two or more objects. And that makes sense. Okay, let's do a couple of examples. Even though I'm sure you already got the idea, but let's do a couple of examples. Suppose you have $8. If you want to be very specific, American dollars. And you give $1 to the same person each day of the week until you run out of money. Okay. Show that there exists at least one day that will be repeated. So there's someone out there that you have $8, and that's all your money, $8. Each day you give this person $1. So let's say today you give them $1, next day you give them $1, next day you give them $1 until you run out of money. Show that there exists at least one day that will be repeated. Well, will there be a day that's being repeated? Well, let's think about this carefully. Solution. How many days are there in a week? 7, right? And then you have $8. Okay, so another way you can look at this is you have 7 boxes. Here's one box here. Copy this. Here's another box here. Here's another box here. Here's another box. Another box. Another box. 1, 2, 3, and another box. Let's put the box here. Okay. Each box is labeled as Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday. So those are your boxes. Those are your boxes right there. Your $8, you can consider that as your objects. You could consider that as your objects. Okay, so each day you give $1 to this person. Okay, so let's say we start off, today's Tuesday. So let's say you give $1 here. That's 1. Give $1 here. That's 2. Give $1 here. That's 3. Give $1 here. That's 4. That's 5. That's 6. That's 7. And then here's the 8th dollar. Instance, it is the day that you begin giving that person $1, which is Tuesday. It could have been Friday if you started on Friday, right? Because if you start on Friday, then you start here and go in this direction. And again, Friday will be repeated if you started with Friday. I'm assuming that's what you meant by F. But in this example, we started on Tuesday. So Tuesday was the day that was repeated. So another way of looking at this is your objects are your pigeons, and these are your pigeonholes, or the boxes. The boxes are your pigeonholes. So I could have just said, by the pigeonhole principle, we will have at least one day that will be repeated. Oh no, we're looking at it. This person will be given at least $1. Will be given $2. You're not literally giving them the $2 on that day, but you know that because one day is going to be repeated, and technically overall that day they were given $2. Does that make sense? Any questions on this? Any questions? Do more examples, but I just want to make sure you guys have any questions. No? Okay. Let's try another example. Did I misspell pigeon? I did misspell pigeon. You're correct. Thank you. That will bother me. Pigeon. Where else? Right, pigeon. Right here. Thank you. I was going to misspell it again. Pigeon. Yes. Yeah, and then pigeon like the bird, or yeah, or like some people call them rats with wings. I don't know why, but that's what they call them. All right, I call them pigeons. They're just pigeons to me. Okay, let's try another one. Show that. Yes, I think people do eat pigeons. Show that if 7, it's a specific culture though, 7 integers are selected from the first ten positive integers there must be at least 2 pairs of these integers with the sum of 11. Okay. Show that if 7 integers are selected from the first 10 positive integers, there must be at least 2 pairs of these integers with the sum 11. So let's write this out. Show that if 7 integers are selected from the first 10 positive integers, there must be at least 2 pairs of these integers with the sum 11. Show that if 7 integers are selected from the first 10 positive integers. So while we're reading this, obviously I'm reading it a bunch of times because I'm trying to understand it. And that happens in math. You really have to read a bunch of times. Show that if 7 integers selected from the first 10 positive integers. So that means I'm looking at the first 10 positive integers. So I'm looking at 1, 2, 3, 4, 5. Those are really small. You guys can't see that. 2, 3, 4, 5, 6, 7, 8, 9, 10. Yes, you can have these in your head, but it's better to write them out because it gives you a better feel or better understanding how you could possibly solve this. So first 10 integers. Now we are caring about which ones add up to 11, right? So that if 7 integers are selected for the first 10 positive integers, there must be at least 2 pairs of these integers with the sum 11. So let's look at these as pairs now. So let's look at them as pairs. So we have 1 and 10, 2 and 9, 3 and 8, 4 and 7, and 5 and 6. All of these add up to 11. Does everyone agree with this so far? Yes. Now, I'm not saying your solution is wrong, Tyler. It's fine. It's just there's something that we have to deal with first. But does everyone understand what we're doing here? We're just getting the pairs. Okay. Now I'm going to do this part here. Show that if 7 integers are selected. Oh, that looks. Can you guys see that, or is that too dark? You can see. Okay. What about this one? Okay, we guys say it's fine. I'll just go back. I'm trying to avoid using yellow because it might be too bright. Okay. So 7 integers are selected. Now that's interesting. 7 are selected, but they're selected at random. They're not telling us that the first 7 integers are selected. They're telling us that we're randomly selecting these integers. It doesn't say randomly, but it's implied because it doesn't say the first 7. It just says 7. Okay, so let's start selecting our integers. So let's select the 7 integers. I'm going to choose one from each one. 1, 9, 3, 7, and 6. And then I'm going to stop. 1, 9, 3, 7, 6. Okay, so I selected this one, this one, this one, this one, and that one. But how many integers do I have so far if I just selected one from each pair? I know it's an obvious answer, but I'm still going to ask it. How many integers do I have selected so far? 5, but I need 7, right? Well, here's where the interesting part happens then. Because I have to select 7 integers, notice that I'm going to have to select 2 more from either one of these pairs. So let's say I select, which one do you guys want to select? Pick any. It has to be a 2 of them. So which one should we select? Well, let's say we select 2. Okay, 10 and 5. Let's select, we say 10. Well, here's 10, and then we select 5. 5. Notice that we have to select, again, from these sections, from these boxes. You can think of it that way. But notice that we already picked 1 in 6. So we know for a fact that this list will contain 2 numbers that will have a sum of 11. Because we have no choice but to select another one from one of these pairs. Well, 2 more, I should say. We have no choice but to select 2 more from one of these pairs. So that's what I'm going to write out. We have no choice. but to select two more from the set we have already, from the set of pairs that sum to 11. Thus, by the pigeonhole principle, actually, by the set of pairs that we have that sum up to 11, we have already selected an integer from. Thus, by the pigeonhole principle, we will have at least two pairs that sum 11. And we're done. And that does make sense, because if these seven integers are picked at random, I'm picking one and I'm trying to make sure they don't sum up to 11 intentionally, then I'm going to pick one from each pair. But that's only 5, which means now I have to pick 2 more. Now I'm assuming no integers can be repeated. Good. Any questions on that? Any questions on that? We'll do a couple more examples. What part? Please specify. What part are you confused on? On what do you mean by having to add the extra 2? The extra 2? Did I add an extra 2? No, I didn't add an extra 2. Oh, on what you mean by having to add extra 2? Oh, okay, okay. So you're talking about, are you referring to this part? Okay. Well, the idea is that I have to select 7 integers. So if I select one integer from each pair to intentionally have numbers that don't add up to 11, then I only have 5 choices. I shouldn't say I only have 5 choices. I only selected 5 integers. That's it. So, but I want 7 integers, because that's what it says. 7 integers are selected. So that means I need 2 more. But if I'm going to select 2 more integers, notice I have to go back to these pairs and select 2 more. So I'll select 10 and 5. But by selecting those 2, they came from a set of pairs that add up to 11. So because one's already selected and now I'm selecting 10, for sure this is going to have 2 numbers that add up to 11. And then because I select 5 and I already selected 6, that's another one that adds up to 11. So I at least have 2 pairs of integers that add up to 11. So in other words, I had no choice but to pick 2 more from this set. That's what I'm trying to say. In other words, I couldn't pick it from any other set because there's no other set of numbers, because I've written down all the possible first 10 numbers, first 10 integers. Okay, sweet. Let's do another example. Okay, example. Suppose on the last example, so the same thing with the, oops, sorry. No. So suppose on the last example that had to deal with the dollar, that had to deal with $8. So not literally the last one, but the one that had to deal with the $8. The money was given throughout a 3-day period. So now instead of the entire week, where you give $1 each week, each day of the week, you give $1 but during a 3-day period. Let's say Friday, Saturday, and Sunday. It could have been any days, but let's just pick specific days just to make it simpler. Okay. What is the least amount that someone will receive? What is the least total amount that someone will receive on one day? What is the least total amount that someone will receive on what is the most amount, what is the least total amount one will receive in at least one of these days? At least one of these days. What is the least total amount that someone will receive? No, I shouldn't say least, I should say most. What is the most total amount that someone will receive in at least one of these days? Okay. So here we go. So now we're giving it to our 3-day period. So what is the most that someone will receive in at least one of these days? And what I mean by the most, in total completely, once all the money is gone. Well, we have Friday, Saturday, and then we have Sunday. Let's say we give $1 to someone on Saturday. That same person now gets on Sunday. Then they get it on Friday. Then they get it on Saturday again. On Sunday again. How many dollars have I given? 1, 2, 3, 4, 5. So I need 3 more. 6, 7, 8. So what is the most that someone can receive in one of these days? At least one of these days. In total. $3, right? It'll be $3, right? It will be $3 on Saturday and Sunday. In total, they have received $3 on Saturday and on Sunday. If you sum it up, once you're done. That makes sense. Why does it make sense? Well, because you have in this scenario, you have 3 boxes, but you have 8 pigeons. So that makes sense that amongst 3 boxes, there's going to be at least 2 boxes or at least 1 box that has, in this scenario, 3 or more pigeons in it. And yes, you have a box that contains 3 pigeons. Does that make sense? We're going to do another example, so you'll see what I mean. Okay. Let's try another one. Suppose that 50 balls are placed into 7 boxes, where each box must contain at least 1 ball. Okay. So suppose that 50 balls are placed into 7 boxes, where each box must contain at least 1 ball. What is the max? What is the most? I should say, what is the suppose that 50 balls are placed into 7 boxes, where each box must contain at least 1 ball. Okay, so we have 7 boxes. So here's the boxes. I'm not going to draw all 7 boxes. Well, technically, I do have all 7 boxes already because I drew it with the days right here. So let me just copy all of these. I'll just be quicker. And then I'll just erase the days. Okay, now we have 50 balls. So let's say ball here, ball here, ball here, ball here, 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 and so on. So there's 50 of them. I'll say I didn't draw 50 of them, but I'm not going to. Let's draw one more. Where each box must contain at least 1 ball. So here's this one in here, 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 and this one in here. So each box contains at least 1 ball. Okay. Now, if you keep putting 50 balls in a box, so one at a time, let's say you put this one there, this one there, this one there, this one, blah, 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 and so on and so on and so on. There's going to be a box that will contain how many balls? If you put 1, if each time you put 1 in each one of these boxes until you run out of 50. There's going to be 1 box that's going to contain at least how many? 8, right? It's going to contain 8 balls. Does everyone agree with that? Okay. Now, obviously, one way is to just literally count it. 1, 2, 3, 4, 5, 6. Wait, no, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, and so on and so on. Honestly, that's going to take a while. But is there another way how to do this? There is. To find the least amount that a box could contain, I can say this. I'm going to take 50 and I'm going to divide it by 7. How many times does 7 go into 50 or close enough? Well, it will be 7 times, we get 49. And then we have 1, a remainder 1. So if we add a decimal, this is 1, and then 7, 3, and so on and so on. I don't care about the next part. In the end, I have 50 divided by 7 is approximately 7.1. However, I wanted an answer of 8. Is there a way this can become 8? Is there a function that allows us to do that? If so, what is that function? Right, the ceiling function, that is correct. If we actually done the ceiling function, our answer will be 8. As a matter of fact, if you go to the last one, and I would have taken 8 and divided it by 3 and applied the ceiling function to it, you should get 3. Because 8 divided by 3 is about like what? 2 point something? I don't remember exactly. 2.6. It goes on forever, 2.6. But because we're applying the ceiling function, so 8 divided by 3 is equal to 2.6 forever. But since we're applying the ceiling function, that's just 3. And the idea of this is because this is actually the general idea of the pigeonhole principle. Doing the ceiling function. So this is theorem 6.2.2. The generalized pigeonhole principle. Which states this: if capital N objects, the generalized, are placed into K boxes, then there is at least one box containing at least n divided by k, and within the ceiling function, objects. And that does make sense. With the last example that we did with the whole 50 balls and 7 boxes, there's going to be at least one box that can contain n divided by k objects. Even if you decided to, let's say, okay, I'm going to make sure at least each box has one ball in it, and then I'm just going to select the box in random and put all the rest of the balls in there. In the end, it's going to have at least n divided by k objects. It's going to have way more than 8, but that's the whole point of at least 8 or greater. Does that make sense? And I'll explain it again, just in case you didn't get it. Let's say this rule where each box contains at least one ball. So I put one ball here, 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 one ball, one ball. So all of these have one ball, and I'll do it in green. So you can see that. They all have one ball. Here's the single ball. Okay. Now, even if we chose a box at random, let's say I chose this box here, and I put all 49 balls. No, actually, no. There will be 43 left. If I put all 43 balls in here, and everyone else just has one ball, and now this one has 43 balls. Well, actually, it will have 44 because of the one that you put there before. So this has 44 balls, and this here are the 6 of them. This box will still hold with the Pidgeon principle because this box contains at least 8 or more objects. Does that make sense now? Does that clear it up? So even if you put one in each box and then you chose one box, let's say this one, and put all of them here, at least one box will contain 8 or more objects or 8 or more balls in this scenario. Even if you decide, well, I'll split it in half, I'll put half here of the 43. Well, that means, actually it should be 42. That means that 21, so 23 will be here, 23 will be here, and then one more will have 2 balls in there. Either way, these 2 boxes will have at least 8 or more objects. So it's not breaking the general principle, the general pigeonhole principle. Good. Okay, I'm assuming yes. So let's do another example. Okay. A bowl contains 10 green keys and 10 blue keys. A woman selects keys at random. Without looking at them. I'm going to give you 2 questions. How many keys must she select to be sure of having at least 3 keys of the same color? And then B, how many keys must she select to be sure of having at least 3 blue keys? Okay, so try those 2. I'll give you probably about 4 minutes. Try them out. I don't think it'll take you that long, but try them out still. Well, we'll find out if the answers are the same or not. Give you a couple more minutes. It feels like stats. Okay. You guys ready? Actually, no, I'll give you 2 more minutes. Actually, let's take a break and then we'll come back. That way you have enough time to think about it. Because this is the last example of this section anyways. We'll finish this off. So let's take a 5-minute break and then coming back, I'll give you the solution. I'll pause it here so everyone can see this auto. Okay, and we're back. So let's answer these questions. Oops, typed in the wrong password. Dang it. There it is. Okay. Oh, I need water. Okay, here we go. So how many keys must you select to be sure of having at least 3 keys of the same color? Well, if we count the objects as keys, and then how many keys must you select to be sure of having at least 3 of the same color? Okay, well, here's one way how I could look at it. Picking the first ball could it, well, no, sorry, picking the first key could either be picking the first key can either be blue or red. Let's suppose it's blue. Picking the second key can either be blue or red. Let's suppose it's red. The next one will be blue. The next one will be red. So for sure it has to be more than 3. But then the 5th one, it doesn't matter which one it is, blue or red. Oh, my bad, sorry. Thank you. So the 5th one could either be blue or red, but realistically, it doesn't really matter. Why doesn't it really matter? Because as if it's red, then we have a key that we have 3 keys that are at least of the same color. If it's blue, then we have 3 keys that are of the same color. So in the end, it doesn't matter. So it should be 5 keys. Does that make sense? For the first one, for part A, 5 keys. It can't be 3 for the reason being that if it was 3, then you're assuming that all 3 of them, you're assuming that each time she goes in to select a key, it's going to come out that exact same color. But there's a small probability of that. We want to be able to say, to be sure that she's going to have at least 3 keys of the same color. Does that make sense? Yes, no. Okay. So that's what it means to be sure at least 3 keys of the same color. But isn't the key selection random? It is random. So I'm randomly saying that the first one could be, the first one and the second one are of different color. Same thing with the third one and the 4th one. Even picking at random, all of them being the same color, all the first 3 of the same color, it's a possibility, yes. But we want to be sure that we're going to get 3 of the same color. Just picking 3 of them doesn't guarantee me that I'm going to get for sure 3 of the same color. Or guarantee me that I have 3 keys, but not of the same color. But 5 will guarantee me at least. Because even if they were all blues, you have all 4 blue keys, all 5 blue keys. Good. Okay. How many keys must be selected to be sure of having at least 3 blue keys? Well, this one's interesting because we want to make sure we have 3 blue keys. Okay, so 3 blue keys. The only possible way I can do that is if I select all the green keys first. Oh, I don't know why I said red. I have the word green there. My bad. So I have to make sure I select all 3 green keys first. So those are my 10 green keys. And so you need 13, at least 13. Is there a possibility that you pick 3 blue keys right away? There is. There's a possibility that you pick 3 blue keys. But to guarantee that you're going to have at least 3 blue keys, you must first get rid of the green keys first. And then select 3 more keys, and you're for sure going to pick the blue keys now. Good? It's okay. It happens. Any other questions? Okay. And that ends the section on 6.2. I always forget that, the sections. Okay. So let's now do section 6.3. But I just want to make sure, again, everyone good with these 2 last examples. I'm assuming yes, because no one said anything. Okay. Sweet. Now, let's go to section 6.3. Dang it. There it is. Okay. Let's start off with 2 examples. In how many ways can we arrange four cards? And the cards that I'm talking about are hearts, clubs, spades, and diamonds in 3 spots. And then we have the next example. In how many ways can we select 3 cards from a 4-card deck? We get hearts, clubs, spades, and diamonds. Just trying to keep it simple for right now. You'll see why in a sec. Let's call this A, and let's call this example B if you want. That way I can So keep them different. Now, I'm sure you already know the answer for A, at least. For B, you may not know the answer. But let's say you know the answer for A. But I'm going to do it the long way, just so you can see the difference. So let's look at A. In how many ways can we arrange? I can't believe I forgot the word can. Can we arrange 4 cards in 3 spots? So let's look at this. So we have 3 spots. 1, 2, 3. Right? I can do hearts, I can do clubs, and I can do diamonds. Awesome, awesome. But I can also do hearts, and then diamonds, and then clubs. Right? Or I could do hearts, spades, and diamonds. I could do hearts, diamonds, and spades. Does everyone agree with that so far? I can also do hearts, spades, and clubs, or I can do hearts, then a club, and then a spade. Or the first one could have been a diamond, then a club, and then a heart. Or it could have been a diamond, a heart, and a club. Could have been a diamond, a spade, and a club. Or diamond, a club, and a spade. Or it could have been a diamond, a heart, and a spade. Could have been a diamond, a spade, or a heart. Or it could have been a spade, then a heart, then a diamond, or spade, then a diamond, and then a heart. Could have been a spade, a club, and a diamond. Could have been a spade, a diamond, and a club. It could have been a spade, a heart, and a club. Or it could have been a spade, a club, and then a heart. Or I could have first chosen the club first, and then the spade, and then the heart. Or the club, then the heart, and then the spade. Or the club, the diamond, and the spade. Or the club, spade, and then the diamond. Or the club, the heart, and the diamond. Or the club, the diamond, and the heart. And I think I read in all possibilities. How many ways can we select? I mean, sorry, how many ways can we arrange? Because we're arranging, right? And I can arrange them in how many ways? I'm sure someone already knew the answer to this. So how many ways is this? Well, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. 24 ways. Or another way of finding it, which I'm still sure someone of you did, is 4 times 3 times 2, and that's pretty much it. Yes, I know I could have done 4 times 3 times 2, but there's a reason why I'm doing this. But does everyone understand that part so far? Any questions? Any questions? Yes, no? Any questions? Okay. What about part B? Let me write down part B here. Part B. In how many ways can we select 3 cards from a 4-card deck? Okay. Suppose we have select the hearts, then I select the clubs, and then I select the spades. Sweet. So there's 3 cards that I selected. I could also have selected the clubs, the spades, and the diamonds. Or the spades, the diamonds, and the hearts. Or the diamonds, the clubs, and the spades. But that's it. Why can't I do the hearts, spades? Why can't I do the hearts, the spades, and the clubs? Because this selection is the same as this selection here. They are both the same. I know that's not proper notation, but I'm just trying to express it. Both of these are the same thing. I already selected a heart, I already selected a club, and I already selected a spade. So what we really have is only 4 ways to do this. We don't write HSC because it's already the same as HCS. But before I go on with this, do you see the biggest difference between both of these? One of them is an arrangement. The other one is a selection. But there's also another big difference. Notice that here we cared what the position was of the hearts, the spades, and diamonds, right? What about hearts, spades, and diamonds? I have it right here. Hearts, spades, diamonds. So notice that when we were doing the arrangement, we cared which one was in which position. We care which one we selected first, then second, and then third. That's why these are not the same. Because that's how we have 24 possibilities or 24 ways. Because I could have chosen this one first, and then this one, and then that one, in terms of arranging them in 3 spots. Here, I don't care about arranging them. I just care about selecting. So I could select 3 cards. What about diamonds, hearts, and clubs? Diamond, hearts, and clubs. Am I missing that one? I am. No. Wait, diamonds is, oh, you know what? That was supposed to be a D. I don't know why I put P. But then that means that this is the same thing as that one. So diamond, hearts. So I can't write this one because these are the same. So I messed up there. So it should be the one I'm missing. Diamond, hearts, and clubs. Thank you. That's the one I'm missing. I have no idea why I wrote CSP. That didn't even make any sense, but thank you. But with this one, when I'm selecting it, once I select hearts, clubs, and spades, it's the same thing if I would have selected hearts, spades, clubs. So I only write it once. Same thing with diamonds, heart, and clubs. I'm not going to write hearts, diamond, club because I'm selecting 3 of them. And it doesn't matter which one's picked first, second, or third. So They're all the same. Or no, another way of looking at it is here, order matter, while here, order does not matter. Does that make sense? So I repeat myself again. Here, order does not matter because these are exactly the same thing. However, here, order did matter because these are not considered the same. Now, when order matters, that is known as a permutation. When order doesn't matter, that's known as a combination. And that's what this section is about, permutations and combinations. But any questions on example A and B before I move on this concept? Yes, that's what we're going to talk about. Yes. Yes, we're going to be talking about that in a sec. But any questions on these examples? Because they kind of explain the idea of what a permutation is and what a combination is, or the differences. Okay, I guess not. So let's write down what these definitions are. So a permutation. A permutation of a set. Gotta space that out. Of a set of distinct objects is an ordered arrangement like how we did the one with the select 4 cards in 3 spots. Obviously, hearts, diamond, club was completely different than hearts, clubs, diamonds. Because we are caring about the order. So the order matters here. If N and R are integers. So if N and R are integers, with R being greater than or equal to 0, but less than or equal to N, then P of N comma R is equal to N factorial over N minus R factorial. That's your permutation. Another way of writing this, which you will see me write often, is NPR. Oh, that's cute. NPR. So if you see me write NPR like that, obviously I'm not talking about the radio station. I'm talking about the permutation. So if we go back to part A, which was this one, this is a permutation. So the way we write it, we write 4P3. We have 4 objects, and we're going to permute 3 of them in 3 ways. So that's the same thing as saying 4 factorial over 4 minus 3 factorial. That's the same thing as saying 4 factorial over 1 factorial. But that's clearly 4 times 3 times 2 times 1 all over 1. And that's the same thing that what we got earlier. If you cancel out the ones, you get 4 times 3 times 2, which is simply 24. So that's a permutation. So if you see NPR, that's what it means. It is a ratio of n factorial over the difference of n and r factorial. Any questions so far? Accidentally touched it. Now, a combination is this. An R combination of elements of a set is an unordered, it's an unordered selection of R elements from the set. An R combination of elements of a set is an unordered selection of R elements from the set. So again, they're not being ordered. Ordered doesn't matter. So the number of R combinations of a set with n elements where n is a non-negative integer with R being greater than or equal to 0 but less than or equal to n equals, and this is how we do, NCR, which the book will write it as C of n comma R, but the way I'm going to write it is this way, NCR. This is equal to another ratio, n factorial over n, the difference of n and r factorial. But the biggest, so it looks very similar to that of the permutation. The difference is on the denominator, you have also r factorial. So going back to B, where we had to select 4, we had out of 4 card deck, we had to select 3 cards. So 4, choose 3. That's another way of saying it, which is 4 factorial over 3 factorial times 4 minus 3 factorial. This is 4 factorial over 3 factorial times 1 factorial. Now to solve these, what I'm going to, by hand, what I'm going to do is I'm going to expand 4 factorial to the biggest one of these. So for example, that one I'm just going to say 4 times 3 factorial, leave the 3 factorial and the 1 factorial is just 1. And the reason why I'm expanding to 3 factorial is because notice that these are the same. So they're going to cancel each other out. So all I'm really left with is just 4 divided by 1, which is just 4, which is the answer that we had earlier. 4 ways, 4 ways. We're going to do a couple of examples of these, obviously, because you got to tell when do I do this and when do I do this. But any questions? so far? Any questions? Right. That fell. No questions? All right. So let's do a couple examples. In how many ways? Well, actually, let's start with this example here because I do like this one. The drama club has 40 members. Doesn't and choose R equal and choose n minus 1, n minus R. It should. So an example that will be, because I'm trying to visualize it. Say we have 5 choose 3. Does that equal 5 choose 2? Yes, that is true. It is. That's a true statement. Okay. Oops. I don't know why I put question mark here. The drama club has 40 members. I was questioning the drama club. Okay. How many ways are there to choose 3 members of the club to represent them? And then part B. How many ways are there to choose 3 members for a president, vice president, and treasurer of the club where no person can hold more than one office. So let's look at these 2 examples. Give you a minute to write these down. And now let's talk about them. So let's look at part A. The drama club has 40 members. So we have a drama club with 40 members. How many ways are there to choose 3 members of the club to represent them? So my question to you is this. Does it matter who are these 3 members? Does the order matter, in other words? Does order matter? No, order doesn't matter. Nowhere does an importance of order matters here. So because order doesn't matter, if I select James, Niels, and then Lupe, is the same thing as saying Lupe, Niels, and James. Order does not matter. So this is a combination. So I'm going to select those 3 people. So I'm going to say 40 C3. 40 choose 3. Does that make sense? So that means we have 40 factorial over 3 factorial times 40 minus 3 factorial. Right? Well, that's just simply 40 I need more space, actually. Let me give myself more space. So that's the same thing as saying 40 factorial over 3 factorial times 37 factorial. That's the same thing as saying 40 times 39 times 38 times 37 factorial. I'm going to stop at 37 factorial because I'm going to reduce it with that 37 factorial on the denominator. 3 is just simply 3 times 2 times 1. Notice that this 3 can go, can a 3 go into anything? Into 39, 13 times. 2 can go into 38, 19 times. So what we really have is 40 times 13 times 19, which is a lot simpler to calculate. That's going to be 9,880 ways. So if you actually sat down and wrote all of the possibilities, you have 9,880 ways how to do this, or how to select 3 members. For 3 positions. Any questions? All right, let's look at the example on the bottom. How many ways are there to choose 3 members for president, vice president, and treasurer of the club, assuming no person can hold more than 1 office? So in other words, not a single person, let's say Lupe, cannot be president and vice president at the exact same time, or president and treasurer at the exact same time. So in this scenario, does order matter? Does it matter who's president, vice president, and treasurer? Yes, order does matter here. Order matters. Because it matters who's the president, it matters who's the vice president, it matters who's the treasurer is. So because order matters here, this is a permutation. So there's 3 positions. So 40p3. That's the same thing as saying 40 factorial over 40 minus 3 factorial. That's the same thing as saying 40 times 39 times 38 times 37 factorial. I'll stop there, over 37 factorial. But in the end, that's the same thing as saying 40 times 59,280. Notice that's way more than a combination. And it makes sense, it should be more than combination because order matters there. If order didn't matter, then that number should have been smaller. But any questions on this? Now, I know there are in your calculator that you could use and choose, and you could do NCR and MPR. Make sure you know how to do those. But in the end, if I give you a problem like this, I want to see at least this. I don't really care about the solution because this is probably the most important part here. Obviously, if I tell you not to use a calculator, then you're going to have to do it like this. Okay, let's do another one. How many bit strings of length 12 contain exactly 3 zeros? How many bit strings of length 12 contain exactly 3 zeros? Well, let's look at this. So I have a bit string of length 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Has to contain at least, no, it has to contain exactly 3 zeros. So I could put a 0 here, I could put a 0 here, and let's say I put my 0 here. Now, let's say I copy this. And let's say I do this. I switch this 0 to here. Switch. I switch this one to here. And I switch this one to here. Is this any different? Is this bit string any different from this one? No, you're right. No, it's not. So does order matter here? No, order wouldn't matter. So because order doesn't matter, is it a permutation or a combination? It's a combination, exactly. So first, we're going to select the positions of those zeros. So the positions of those zeros are 12, choose 3. And this will represent the 3 positions being chosen for the zeros. That's what this is representing. So out of 12 positions, I'm selecting 3, any 3, where I can put zeros. That's it, right? Next, we choose the zeros, because this only worries about the positions of the zeros. Now, next, I'll write this down. We need to choose zeros. Well, how many zeros are there? Well, there's only 1 0. because there's only one way of how to choose zeros, right? There is only one way on how to choose, how to do that. And so it is 1 times 1 times 1, which is 1 cubed. There's only one zero, and there's only one way on how to pick zeros. So if I pick a zero here, how many ways is there to pick zero? 1. How many ways is there to pick zero? 1. How many ways is there to pick zero? 1. But now I also have to worry about the other positions. What are these going to get filled with? Well, lastly, how many ways can we arrange the ones? Well, we know it has to be ones because it's a bit string. In a bit, it's only a 0 or 1, nothing else. So we have this position here has to be a 1. How many ways is there for 1 to be selected? Well, 1, because there's no zeros. All the zeros have been used up. How many there's this position, how many ways? 1. This one, 1. This one, 1. This one, 1. This one, 1. 1, 1, and 1. So in the end, there's 9 positions, and each one has one way of being arranged. So, well, that is 1 to the 9th. That doesn't look like a 9. So our solution is 12 choose 3 times 1 cubed times 1 to the 9th. Which in the end, that's just 220. Does that make sense? Any questions? Any questions? No? Okay, let's do another example. In how many ways are there to select a first place, second place, third place, and fourth place winner? In a race of 100 runners. No ties allowed. Okay. Now here, does order matter? Yes, order does matter. So in this scenario, it matters who's first, second, and third, and fourth. So we need a permutation. So my solution is 100p4. That's it. So it'll be 100 factorial over 100 minus 4 factorial. That's the same thing as saying 100 times 99 times 98 times 97 times 96 factorial. And I'm going to stop at 96 factorial. Why? Because the denominator simplifies to 96 factorial. So I'm going to cancel those out. So I'm just left with 100 times 99 times 98 times 97. In the end, this is going to be, well, I don't know what that answer is actually. I didn't even bother multiplying it up. But that's going to be my answer, whatever that is. Any questions? No? All right, we'll do one more. And this one, what would it look like with ties? If it was ties, then we have to take some things to account. We will have to take to account if they all tie for first place, that will happen one way. If they all tie for second place, third place, and fourth place, that will also happen in one way. But there's also the possibility of them tying for first place, and then there's a second and third place. Then there's a possibility of them tying for second place, which means there are going to be two clear winners for first and fourth, but they tied for second. Then you have to do the same thing with third and the same thing with fourth. That's what I think it's going to look like for ties, if ties are allowed. So if no ties are allowed, this is going to be it. Now, how will we do that one? 100 piece of 4. Suppose they all tie for first place. There's only one way you could do that. Yeah, there's only one way you could do it. Plus, there's a tie for second. There's only one way you could do that, but that means someone won for first place and for fourth place. So 100 piece, no, not 100. It will be 98 p sub 2, because it matters who comes in first and who comes in last. But that's the thing. If you tie for second place, I'm assuming only 2 people tie for second place. It could be 3 people who tie for second place. So then plus, there's only one way you could do that, but then who won the first place? So 97 p sub 1. Two people tied for second. No, not 2, 3. Plus, then there's a tie for third. Let's assume 2 people. It'll probably be the same idea. 98 p sub 2 Well, two people tying, there's only one way that could do that. And then 98 P sub 2. But then what if all three of them tied for third place? No, but see, you can't tie for third place for all three of them. Two people could tie for third place, but that's it. Not all three of them. So that means there's only going to be a first and second place winner, plus tie for fourth. Well, that means that there's only one way to do that, assuming two people tied for, well, you can't tie for fourth. It's not possible because it's either first place, second place, or third place at that point. So fourth place couldn't be tied. So I will say it will have to be something like this. I will need more time with this one, but I will have to say something like this because the possibility of choosing four winners is here. Tie for first place, there's only one way you could do that. That's all, if all of them come in. No, wait, is there one way? I don't know what just happened there. That was weird. There we go. Wait, I don't think it is one way. Tie for first place. Because you have to get if you tie for first place, that means everyone that means four people. Well, actually, no, because then that's an issue. How many people tied? Was it all 100 of them? You see what I'm saying? It gets a little bit more convoluted now that I think about it. Because it's a possibility, it's an extreme rare possibility, but all 100 of them crossing the line at the exact same time. And there's one way how to do that. There's also the possibility of 99 crossing them all at the exact same time, and one did not. And that means that person is second. They're 97. Do you see what I mean? So it's going to be a lot more than what I wrote here. It's going to be way more than that. But yes, you will have to add the permutations because now you're looking at all those possibilities. But yeah, if ties were allowed, it's gonna be brutal with 100 runners. If it was 4 runners, it'll probably be a lot simpler to do because it's much simpler to like map it out. Does that make sense? It's an interesting question, actually. Questions? Yes, no? Okay, so we run out of time, obviously. So we're pretty much done with this section. We'll do, so I posted a homework for this section on Canvas. Other than that, I'll see you guys next time. Pretty much have a good weekend. All right, take care. No, it's just me towards, I was literally trying to figure out what will happen if all of them tie. But you're looking at, because there's so many runners, you have to look at so many possibilities now. Like what happens if all 100 tied? What happens if 99 tie? What happens if 98 ties, 97, and so on and so on.